Hi, Doug Littrell again. This will be video number 27. It's July 3rd. Once again, I have the camera in my phone tilted so I can get my head in. Try to get this as wide as possible at the same time. Gonna record some more data. The reason I call it data is because it's raw. These are raw observations of nature. Even though we're using some man-made objects are involved, it's still, these are raw, natural universe dynamics that we're observing here. Of course, we're observing them in the Earth's atmosphere at a certain amount of gravity, etc., etc., but we're just as much a part of the cosmos as anything else out there. Anyway, you know, and this is what's going on right here at this moment. You know, if you had another planet, similar gravity, similar atmosphere, even if it varied by quite a lot, you could still do a lot of these same things. We have no control over how these things happen. We just have to observe them and then try to figure out what's going on. What are the laws behind these occurrences? You know, right now we have an interpretation. We've had it for quite a while. I guess the first fifth ball experiment was done something like 1600, and it's been interpreted that negative charge exists. I'm contending, and I have an entire atom model without negative charge. I'm contending that negative charge does not exist, and I'd like to prove it. You know, we have this attraction. We've been rubbing this wand with this cloth, and you know, we have this attraction such as that, as you can see, this plastic ball. This one as well, it's heavier. Now I've added a piece of wood dangling in place of where the copper ring was, so you can see the wood is attracted to it. You know, should this be interpreted that positive and negative charge are what's causing this? Is that the only way to interpret this? The only way to hypothesize or suggest what's really going on? Let me just tell a little bit more about what's been going on. I made a little copper donut, you might call it, hammered it out. Well, this one is actually a strap that holds copper pipe, and I found out it actually is copper coated, but it has iron in it because it reacts to the magnet. So I had to take my copper ring and cut a section out of it and smash it by hammering it, drill a hole in it, and I've got one that's pure copper, and it's not at all attracted to the magnet. By the way, there was a YouTube video or some video I saw once where a magnet, I think it was a magnet, was dropped through a copper tube, and it did pause. So we probably shouldn't say that copper doesn't react to a magnet whatsoever. That's probably false. That's probably been disproved. But anyway, I attached this in place of the copper ring, and then when I found out it was reactive to the magnet, I had to get rid of it. And then when I attached the other one that was pure copper, I tried the magnet back and forth, and I couldn't get it to move. It seemed like to me the shape of the copper, the ring, interacted well with the magnet moving back. You couldn't see in the video too well, but the copper ring was actually turning, swiveling back and forth as I moved this. And it could be due to a very, very mild attraction. Now, it wasn't enough attraction to pull the copper over to the magnet, but there may have been enough to cause that. So we're not going to conclude that. But keep this in mind too. that what we're doing right now with our interpretations in science, though we are so amazingly adept at doing so many things in science now, it's just incredible. There's so many things that have been explored, achievements that have been made. It's astounding. But still, our basic interpretations of nature could still be off, and that's what I'm trying to suggest and then prove and explain. For example, okay, I'm saying that photons with mass, a certain middle charge type, there being no negative charge, just no charge to low charge on up to high charge. And that's all that really exists, and everything can be explained from that alone. So we would have these middle charged photons that are some of the same photons involved in visible light, flowing out one pole of the magnet into the other. And of course you would have other particles from the environment also coming in, so there's liable to be eddies there to some extent. But what I wanted to mention regarding that is that when you use visible light in lasers to cut steel, and you're going to tell me that the light has no mass, I'm going to say that's wrong, okay? Because you can use a laser to cut steel, and that's just light, and it would have to have mass to do that. That's just one example of, I could probably name many more. How radio, for example, it's not supposed to have mass, yet it's blocked by buildings, it's blocked. It deflects up in the upper atmosphere in funny ways sometimes, and that would all require mass, in my opinion. I want to mention cloud chambers with regard to this too, because cloud chambers would really be a good analog to what we're doing here in a lot of ways. You get indications in science, and you should keep all of those in mind while you're considering other things or certain questions. You should always keep your data readily available in your, whether it's in your mind, your notes, or whatever, so that you can refer to that as for guidance or for help in making an interpretation. Well, that should be done in this case with cloud chambers. Everything should not be kept separate, or you know, to some extent sterile. You know, like everything is individual. Everything is related. Everything is related. Everything is somehow related to everything else, or in several ways. But anyway, in a cloud chamber, this is routine. You can observe this in videos on YouTube. Thorium or radium or various kinds of radioactive substances, they might put them up against the side of the glass of a cloud chamber, let's say, and inside there's alcohol has been evaporated so that it's heavy in the atmosphere inside the cloud chamber. It's just loaded with alcohol molecules, and of course it's transparent. You can see right through it all, just like you do when you're looking through gas molecules in the atmosphere all around you. You don't see them. Same thing with the alcohol in the cloud chamber, but they've got it trapped in an enclosure. I would usually glass, of course, and then you can take radioactive material, put it next to the glass, let's say, and it will fire whatever emissions are coming from that material, whether it's an alpha particle or a beta particle or a gamma photon, gamma emission. They will pass through the glass, and they will go into the cloud chamber, and then the cloud chamber will mark their path. The reason it happens is very much related to this, what we're doing here. The alpha particle goes a very short distance, maybe a couple of inches, if that, something like that. And then it knocks off electrons, or I would say radio particles, from shells. It knocks off the orbiting hovering particle shells, some of the particles that are surrounding these gas molecules, like diatomic nitrogen, diatomic oxygen, or what have you, that are just there, and it knocks those off while passing through. It's moving fast, it runs into them, and what happens is you see a cloud that marks the track. And the reason you see the cloud is because the gas molecules, when they lose some of those orbiting hovering particles, now they're not satisfied, and so that their nuclei attract other gas nuclei, because they're not made copacetic with the environment, you might say, or neutralized with the environment enough. And so they when they lose, some of those are knocked off temporarily, they pull together and they make a little cloud, and the cloud is a little streak. Okay, and when you see a beta particle moving through that same environment that's emitted from a radioactive substance, now it goes quite a bit farther, a foot or more through the cloud chamber, something like that, and it also makes a cloud streak, and it's doing the same thing. It goes much further because it's much smaller, and so it's not having as many encounters as something that's much, much larger, like the alpha particle. And it moves through the cloud chamber, and it knocks off a lot of electrons. Well, we call them electrons. I would say they would be radio particles in shells, because I don't think those small gas molecules, those atoms, are large enough to have what I would call an electron proper, like another beta particle. So as a beta particle moves through there, a foot or 15 inches or whatever it is, a cloud is formed. Some of those particles are knocked off. Now the nuclei that those surrounded that were knocked off are putting a call on the environment to replace them, and the nuclei actually attract to one another more, and then they pull together. And when you have more concentration of these gas molecules, now it becomes opaque. Okay, that's what's happening in cloud chambers. And we won't really go into the gamma photon. When it goes through, it goes much farther because it's much, much less mass. It does collide, and you can see a very slight streak. It might go clear through to the other side of a fairly large cloud chamber. It might even exit the cloud chamber, but there is some indication that it's traveled through it, and that it has made contact with some gas molecules, and there's a very slight trace of a streak of a cloud from the gamma particle. I'd call it a photon, a high charged photon. Anyway, as far as more data on this, I took glass this morning to see if I could get it to be reacting. And you've already seen the wood reacts. It's highly attractive to the PVC wand. I tried a heavier PVC wand. It worked it also. I prefer the thin wall. As far as I tried wood earlier this morning. This is just a back scratcher you buy at a dollar store. It's got varnish on it though. I don't know if that makes any difference. Maybe. You rub that very aggressively, but try to get a reaction, and there's absolutely nothing with the wood. Now the wood responds to this PVC that's been rubbed, But now when you reverse this and have wood as the wand, of course this would be wood to wood. I'm not seeing anything. With wood as the wand. Now, wood would have a lot of carbon in it. We know this has PVC has chlorine and lots and lots of chlorine, like 57% is chlorine. Well, the carbon atoms in the wood, or we know there are carbon atoms in the plastic ball here. I'm not seeing any attraction, so that's just take a note of that. I also used glass. I found this glass tube in the basement, and I didn't have much to choose from for glass. I've got a few vases, but this is a little funny little tube I had bought at some thrift store or something that I thought was unusual, looked kind of scientific, so I bought it. I think I did use it for one time that I was checking into. Anyhow, we'll rub this glass. And when you look on Wikipedia, it almost looks like when they did this experiment in the 1600s or whenever they first started doing it, that they would rub glass. I mean, it looks like they're showing glass as being the thing that's rubbed and gets charged up, so to speak. But when you rub glass, I'm not seeing anything. I mean, that was already swinging. Uh-oh. The wood did retract to it. Looked like. Okay, well then maybe it is possible to get the glass to be reactive a little bit. But it's nothing like the PVC. Boy, the PVC is the champ so far that I've found of this. Yeah, there's an attraction there. The glass did work with the wood. There's a little bit of attraction to the hollow plastic ball too. Okay, so I wanted to explain a little bit more about cloud chambers, you know, lasers, other things we know about in science compared to this, and then I wanted to tell a few more things I've tried. The wood didn't work at all. Well, that's with varnish on it. The glass almost didn't, but did a little bit. You know, I wanted to tell, you know, a few more things I've been trying. So that's video number 27. Okay. Just to double check the wood, rubbing it like the wand. I went out in my garage, I found an unvarnished board. So I'm rubbing it, trying to get it to react. So we're just gonna see if we can make a conclusion about the wood as far as rubbing it to cause this effect. Nothing. The ball was already swinging a little bit. It's nothing. Nothing there. Nothing to speak of, less than the glass. Also, I made an error in video 26 when I said nylon strings. doesn't respond. It does. Everything. I needed to mention this too. I made a new bead, a little larger piece of styrofoam wrapped inside aluminum foil, and it doesn't work because the aluminum foil is two-folded. I'll have to get a good round bead and layer it perfect, you know, as well as I can with the aluminum foil. You can't find a point on this bead. It's larger. You can't find the point where it attracts. It will repel, and it also spins around because it's folded. That's what I think. Now there, it's attracting. I could not get that to attract last time. Now it attracts. Now it attracts. Well, that's worth noting. I tell you, I could not find any place on it last time I did this where it would attract. Now it's like acting like the plastic balls almost. That's crazy. So we have no control over this. So, you know, what's going to happen, I mean, you try to be consistent, make your little spheres the same, maybe layer them the same, you know, use similar string. Look at that thing. It's attracted. Oh my, now it's repelling. Okay, now it's working. So there is somehow maybe it's sorted out which side would be its attracted side. But when it's not smooth like that, you have all those cavities and crevices, then it probably what happens is it turns too easily, so you can't find the attracted spot. I think the attracted spot is essentially a hole in the shells. I mean, what we're going to end up describing here is something that happens with the wand, and then relative to what happens with conductors and non-conductors. I've been studying a lot more about conductors lately, the resistance of different metal, you know, elements. It's very interesting. Let me grab that. Anyway, there are some really good tables online that show the periodic table and in relation to resistivity or resistance. One of them I really liked, it had blue, like if it had the periodic table and it had like different shades of blue, and then it would graduate over to green and then yellow and red. None of them, the elements were red or yellow that I can see. So if they were a deeper blue, they were a better conductor. It helped, you know, get an overall view of what's going on with the different elements. How, you know, like I said yesterday, video 26, lead is a conductor, and it shows that lead is a conductor. Now, it's not nearly as good a conductor as aluminum. It's not nearly as good as copper. It's not nearly as good as silver. Silver's the best of all. Gold is very good, but not as good as silver. Of course, the thing about gold that's so good is that it doesn't change. It doesn't corrode, whereas silver can tarnish. So that's one thing they keep in mind when they might employ gold in a system that carries electric current and makes contacts or points or what have you. So they want that to hold up and not deteriorate, and gold is the best for that, even though it doesn't conduct quite as well as silver. But it was interesting. It looked like there were, I wrote it down last night, there were like something like 22, when you go from, let's say, lithium to lead, there was something like 22 elements that were decent conductors by the shade, if you go by the shades of blue that they compiled in that one representation of the periodic table. There was something like in the range of 22 what you might call decent conductors, and those were up to about where lead. You know, for me it was no. These were much better than lead. And then there were about 20 more that were similar to lead, that were probably what you would call fair conductors. And that's just my own rendition of what I saw. You know, that as far as actually applying these things and using them, what you might call a fair conductor compared to a good conductor, you know, it might be a good bit different than what I've just said. But, you know, regarding what I've seen so far, it's very interesting that conductors, there's so many so many elements that conduct electricity. And though perhaps not good enough for us to use them that often, because there's other materials that are in good abundance, like copper, that are relatively good abundance that we can use instead. They just do a better job. That's all there is to that. I wanted to show, let's see, the other thing I want to show is these strings. I didn't show that. The nylon string, I thought wasn't attractive. There you can see it is attractive. The nylon string is attractive, which should be just like a plastic ball, essentially. Now that ball is heavy. But anyway, and this thread that this bead is hanging by, it's attracted. Or you can get it so that it repels. You can get the string to I think. But that may be a reaction with the bead itself carried into the thread. Now the thread is lifted. This is the thread that was used on the first bead, and it lifted that right up. You know, also of course when you get this, after you've rubbed it and get it as reactive as you can get it, you can go across your arm and feel that, and see the hairs on your arm raise up. You can feel that as you move that across. So like the strings, your hair on your arm is attracted. Like now there, it's repelling. The thread the bead is attached to. Now it's attracted there, and on the other side it's repelling a little bit. See what happens now with the bead. There it's attracted. It's attracted. Right now I'm leaning, as far as my interpretation, I'm leaning toward there being different reasons for a material being a conductor. I'm thinking right now that covalence is involved, and perhaps the best conductors. I've seen covalence firsthand with the naked eye and water. When water molecules join, and when you wet cotton fabric, like a t-shirt, and then look at direct sunlight. If it's not overly wetted, you will see those water molecules. And this is how I know I was looking at atoms, because that were attached to the cotton fibers, the ones that had the big rings around that gray dot in the center. Because when I wetted the cotton, I could see the water molecules. And they would make a big conglomeration, and it would just be like a clear conglomeration with a line, a circle. It's just a circle with a line at its edge. And that's all you would see. And then they would eventually separate, and you would see these individual water molecules, and they would, I wouldn't say vibrate, but they would move back and forth slowly, and then they would disappear. So they were evaporating. I was watching them evaporate. But the size of the water molecule, an individual, once they separated and before they evaporated, and the individuals, it was very small in comparison to those large atoms that were, you could see next to them, nearby. So that's another thing I wanted to mention. So I've seen covalence, and you would have to interpret, I believe you would have to interpret liquid water, that when you have joined molecules, there is covalence occurring. And it could be, in the case of copper or some of these solids, that covalence is occurring too, as well, even with pure elements. There may be some type of covalence that makes those materials more readily conducive to being good conductors. And I'm suspecting that's one of the explanations for why conductors conduct. I think another reason is something I already suggested for copper, which wouldn't work out with lead being a conductor. And lead, you would have to have the complete complement of all of the electron shells, maybe even the positron, probably even the positron shell, as the very outermost shell. Those black shells that you see when you view, when you let direct sunlight pass through cotton fabric, and you're looking at it with the naked eye. Some of those large atoms that were attached to the carbon in the fibers, you can't see the carbon. It's so small, individual carbon atoms. I couldn't see those. Or if I did it again, maybe you could see something that you would say, well, that must be a carbon atom. But I didn't notice any of that. But what you could see were large atoms attached to the cotton fibers. And some of them had, my memory, I've written down notes, so I think my memory serves me well on this. They had dark circles, and these were electron shells. These were not radio shells. They were electron shells, because there's fewer of those in the environment, and they can't make spheres around nuclei. But when you move out from a nucleus, you have to have more of those to make a complete sphere as well. So there's a couple of reasons why they don't make spheres. But in some of those large atoms, they had 3 of those dark circles around their gray dot center, you might call it, and then others had 4. And so that's how I came up with 4 electrons in my atom model. You know, you've got the neutrino type, which I believe is a 15 mass unit. You've got the beta 27, which has a orange gamma photon in the center of it. By its mass is only 27. Then you have the beta 43, which has a red-orange in its center, gamma photon in its center. It has more mass because of that. It takes more to cover it over. neutralize it with the environment. And then you have the positron, which has a red in its center. It takes more particles covering it over, therefore more mass to do the job. So anyway, that's more about where I'm going with this. You've got covalence is probably involved in some of the best conductors I'm thinking right now. You've got perhaps what I said for copper in video number 25 occurring with some of those, where you have a partially filled outer shell, radio shell, that is conducive to when you have a plethora of electric photons presented next to it, a nucleus, or next to an atom or shell of an atom that's partially filled, and it's being impacted by collisions, then it makes it more vulnerable for that profusion of electric photons to supplant those that are being basically carrying around because they're being hit. Now, there's another factor involved in conductors, whether they're good conductors or not conductors. Well, it's pretty much true of all, and that is when you lower the temperature, they conduct better. So, you know, my explanation doesn't fit in every way, so, in that respect so far. But that's what I'm coming up with so far, is that not one factor causes an element to be a conductor, but covalence is probably key. A partially filled outer shell that has enough, couldn't be too scant, it couldn't be too overfilled for that to occur if I'm on the right track on that one. And then there's another possibility, I think, that may have to do with some of what's going on here with the static electricity, and that is there's a propensity for the outer radio shells and substances like these, that even when they're not disturbed, once you see, the disturbance happens when you rub the PVC tube. That's the disturbance that gets it started. So then you have electric photons coming in, which repel each other highly. Well, not highly, but they repel each other. And I'll get more into that explanation in video number 28. I could go ahead and, this video is getting a little bit long, so I'll hold off on that. I want to include this with video 27. I've come outside. I've found a really bad place in my yard that where there's a bare spot. Over here by the spruce tree, it's kind of a bad spot. And I've wetted the ground. I've covered a sledgehammer with aluminum foil top to bottom, bottom side all the way up. Let's see if you can see that. And I've got it, I dug down in the mud a little bit and made sure that the aluminum is grounded. Got a wire from my ohm meter, the two pins. Went ahead and put the styrofoam bead that's covered by aluminum foil on this pin. Got it out here dangling. This pin's inserted into the aluminum foil, so it makes electrical contact. There's wind out here, so that's a little bit of a problem. There's an ant on the plastic ball here. Anyway, gonna rub the wand. And of course you can see the wood is highly attracted. just like inside. Orange rubber ball a little bit. The hollow, you may not be able to see the hollow. Let's see. The hollow plastic balls right here. Yeah, there it is. There's wind. Of course, that's attracted. And so we want to see what happens here with this all hooked all the way to the with the conductor all the way to the ground. And of course, it's highly attracted. Now the thing is if you leave it in contact, it discharges. So you get the same effect if you have as the setup with the insulator, where it's insulated from the ground. But it looks to me like it discharges quicker because all of this recoil is going into the ground. And so if you leave it in contact, very quickly, whatever is in this wand after it's disturbed appears to pass into the wire and down into the ground. Now, with the insulated wood, now we know that with the insulated, we've already done this the first day. It was Saturday, video number 26. Covers Saturday and Sunday. This is Monday. These things attached for up to 3.5 hours. And so the connecting it to the ground does discharge it. When they come in contact, it allows the attraction to dissipate. So that's more data for figuring out what's going on with this.